Great. Thanks so much, everybody. It's a real pleasure. I think, Stephen, thank you for organizing this, and I'm really delighted to talk about some work. And some of it goes back, honestly, it connects with decades worth of work that we've been doing. But it's also, I have some completely brand new stuff here as well. And there's been a lot of activity that we've had in the last couple of years in this space. So I'm really excited. So before I start, I'm curious if, I actually can't see the Zoom group, but everybody else can see it. This image, I'm curious if anybody knows, raise your hand on Zoom if anybody knows what that is.
Well, you're not showing an image.
Oh, are you not seeing it?
No.
Oh, no, I just mean the drawing, this drawing. Here on the title. Do you see that?
I see you.
Oh, then I'm not. Oh, I'm sorry. I'm not. I'm so sorry.
To share your screen.
I'm not sharing yet. It looked like it was sharing, but it's not. I'm glad that resolves that question. Okay, here we go.
Here
it is. So I'm going to talk about the theory of human language. You see it now, yeah?
Yes.
Great. So I'm talking about the theory of human language processing in the era of large language models. So my question was, is this drawing, is this woodcut familiar to anybody? Curious. So this is the one of the original illustrations from the novel Great Expectations. And it's a crucial part of the story where this character right here is the protagonist. He's an orphan and he's being introduced by this guy, a lawyer, to his rich benefactor. Now, the reason I bring this up, this is a crucial part of this story. It's a classic of English literature. And later on, the protagonist, Pip, gets surprised. And so I think it's a fun image for me to start with. And one sort of thought-provoking thing is that the word expectation, it turns out, actually has an interesting double entendre in this title, one of the classics of English literature. I think that the meaning that you're all familiar with, this is from the OED, is of course that it means the action or fact of anticipating something or foreseeing it. And that's actually a primary meaning that is going to matter for today in my. But interestingly, expectations actually has this other meaning. At the time in particular, it had the meaning of the prospect of inheriting wealth or property. And that is and so that double entendre is sort of crucial, and ambiguity is rife within language. So this is, I think, is a wonderful example of both the notion of expectation, how expectation and surprise interact in cognitively crucial ways, and also of ambiguity in language. Okay, so we're in the era today of large language models. So what is a large language model? This is transformed technology. It's also transformed language science. So a large language model is a computational architecture that takes in inputs in a sequence of tokens or words, usually words, but sometimes pieces of words, and transforms them successively from discrete units into vector representations, high-dimensional vector representations, which are indicated here with these little matrices. And they're deep in the sense that there are many layers, layer, between from the beginning all the way to the last layer of output. And at the end, the last layer, the words transformed embedding representation is responsible for predicting a distribution over next words or tokens. Okay, so next token prediction is the fundamental processing thing that these language models do. Incredible things come of that. And over the last several years, this has been a remarkable technology for language science. And for example, it turns out that there are correlates of hierarchical discrete syntactic structure in large language models, that you can do a good job predicting brain responses in high dimensions to linguistic input from the embedding representation models. You can also decode possible inputs from the brain representations that allows you to do things like basically like decode thought into language. We use them to connect with behavioral data and confirm law-like behavior relationships between probability distributions in language and processing behavior. And they even have called these neat emergent abilities. So for example, large language models weren't designed to do things like replace letters in a sequence with the letters that immediately are next to them on a QWERTY keyboard, but they do a pretty good job of that on the fly. It's actually not perfect, but it's not too bad. Okay, so these are really amazing technology, and they're stunningly powerful. So, for example, here's an example psycholinguistic task. So, to try to understand what LLMs are doing, I put on my hat as a psycholinguist sometimes, and I take examples that might elicit interesting human processing behavior and see what the LLMs do. So, for example, for all of you, think of how you might complete the following sentence in a way that conforms to the grammar of English. The man who the car. You probably have an idea of how you might complete that. GPT-4 completed this. The man who the car hit at the crosswalk was taken to the hospital immediately. That obviously is a grammatical continuation. Claude 3 is another large language model. Not only does it complete it, also grammatically, it completes in a very similar way to GPT-4, which suggests that maybe the training data sets of these models are very similar. These are both successes. Here's a much harder prompt. This is one that's hard for humans. The monologue that the actor through the movie industry, GPT-4 says, you might have a hard time doing this yourself. GPT-4 says, the monologue that the actor who the movie industry admires delivered was profound. And this looks very weird, but actually it's perfectly grammatical English. The movie industry admires the actor. The actor delivered the monologue. The monologue was profound. So in each case, I've colored the subject and the verb that it is, and its verb in the same color, which helps decode it. These are very hard sentences to understand or produce for humans, but not only GPT-4, but also Claude 3 produce these quite well. So in a way, they actually have, even though language is something that is produced by humans, and it's initially hard to think about what it might be, quote unquote, like superhuman behavior on the part of a computational model. Actually, these models demonstrate instances of apparently superhuman behavior in interesting ways. Okay, so that's one example of sort of these remarkable capabilities of these models. So for today, I don't think we're gonna have time for all of this, but these are some of the things that we try to do in my research. We try to contextualize the successes of LLMs within long-standing frameworks guiding cognitive science. We illustrate how LLMs can help develop general theory of language structure, learning, and use within communication, revisit interrelated ideas about human language processing as rational and expectation-based, probabilistic, and goal-directed action, surprisal theory, noisy channel, human language processing. We're not going to get to uniform information density, but that's also an idea that is related here and that LLMs have helped us revisit. And in a sense, this is all part of a broader enterprise of triangulating on a model of human or human-like language between, we use traditional mathematical symbolic theories of language structure from generative linguistics, probabilistic and computational models from AI, machine learning, and statistics, psychological experimentation, like bringing people into the lab, having them read, monitoring their eye movements, also neuroscientific exploration. And then it's the era of large language data, of course. We now have data sets which are orders of magnitude larger than a human lifetime's worth of experience. And we can use that to train models. And also we can study the structures of language within. Okay. So within this context, sorry. Let me go back. What did I lose? I'm still sharing. Let me go back into this. I wanted to do this, get rid of, I've somehow reversed where the presentation happens. Hold on a second. How do I get rid of that? There we go. That's it. Okay. So I next want to talk about sort of a general idea about the incrementality of language comprehension. In the general case, when you're doing language comprehension, listening or reading, you're in the middle of things. You're in the middle of a sentence, maybe in the middle of a word that's coming in. And in general, there's going to be some preceding input. Okay. There's going to be some preceding input. You're going to be making predictions on the basis of that input, and you'll get current input. The predictions that you've made about that input affect how you process it, and you keep on going. The current input becomes previous input because time is passing and so forth. And expectations arise from many different kinds of information simultaneously. So I might highlight, for example, the role of syntax. Jamie was clearly intimidated. what do you think is coming next? It's probably the word by and then something more abstract, a source of intimidation. And this is actually not a very superficial prediction because the word intimidated, if I just look in corpora, usually the word after intimidated is the individual or group that is getting intimidated, not the source of the intimidation. But because of the passive voice, it actually works in the opposite way in this case. Okay. Phonological knowledge also matters. So for example, in the context of Terrier N, you might predict apple, orange, or ice cream cone. In the context of Terrier A, you have a different set of predictions, nectarine, banana, sandwich. Okay, so this is the interaction of lexical and syntactic and also phonological knowledge. And then there's sort of more generic situational semantic knowledge that seems to play some role, a crucial role everywhere in prediction. So for example, in the context of the children went outside too, everybody, it's obvious that the next word is going to be play. And in the context of the squirrel stored some nuts in it's obvious that the next word is statue. No, it's not. It's the next word is tree. Now I want you to think for a moment, what is actually the place that squirrels store their nuts? It's actually not trees, it's the ground, but people generally tend to expect the word tree here, which tells you that situational, real-world common sense knowledge in language processing does not guide everything. It plays an important role, but predictions and expectations are derived from other information sources, not just common sense. So these expectations from diverse contextual cues affect human language processing extremely quickly. And this sets up desiderata for a theory of language processing. Language processing is robust to noise. So famously, for example, here, you can have cases where you have a passage where almost every word has its letters scrambled, but you can read it nevertheless. It's remarkable because we're robust to errors and mistakes and omissions in the linguistic input. We have mechanisms for that. We have accurate disambiguation. So for example, the women discussed the dogs on the beach. Who's on the beach? There are different syntactic structures for this sentence that explain why there are different interpretations, but we actually are really good at honing in, for the most part, on what people mean. And incrementality. The children went outside to play. You don't have to wait till that last word to form an expectation about it. And also, processing difficulty is differential and localized. So if I take, for example, two very similar sentences, the hiker that the ranger passed got lost versus the hiker that passed the ranger got lost. The first one is the reading times word by word, when we monitor those using what's called the maze task, are in solid. The second version, they're in the dots. And you can see is that word by word differences in how long people take to successfully process these words in reading are different. They're different across words. So the is read faster than a word like past. But also the word the is read differently, is read more slowly in one context than in another context. So that differentiality and localization is crucial for our theory of language processing. And we theoretically tackle the problem of building a theory of how processing and language works in humans through the principle of what's called rational analysis. This is a framework for developing cognitive theories that John Anderson proposed in the really in the early 1990s. And the background assumption is that cognitive agents are optimized via some combination of evolution and learning to solve the crucial tasks for them in an everyday environment effectively. For humans, language understanding, language production are crucial tasks for our success in our environments because we live in social communicative environments. So, given that background assumption, how do we build theories? We start by specifying precisely the goal of the cognitive system. So in the case of language understanding, for example, the goals include understanding what you're hearing and reading, and doing so efficiently and accurately. Formalized model of the environment to which the cognitive system is adapted. That includes characterizing the environment of language, the statistics of the linguistic environment, the structures in the native language, the experience that the language user has, their linguistic background, their knowledge of the local environment, not only the broader linguistic environment, but the environment of the moment, the communicative context, the modality of communication, noise in the environment, for example, if it's a dim screen and you're reading, or if you're in a cocktail party and talking. All of those are parts of the environment. Make minimal assumptions regarding computational limitations. That is, assume that unless evidence suggests otherwise, or other compelling characteristics suggest otherwise, that whatever computational task is facing the mind does a good job at finding the optimal or a near optimal solution. And then derive predicted optimal behavior given these and test them against data. And if necessary, if there are discrepancies between the data and the predictions, then revise 1 through 3 as needed, and then get subsequent incremental adjustments to the predictions and iterate this until you've got a really good match between theory and data. So this is a way of sort of starting point theory development and then testing against data and iteratively refining your theory. And this is what we do. This leads to a view of comprehension as real-time reverse engineering. So the picture is that actually the generative process by which language is produced is that speakers or writers have discourse goals. For example, if I'm in a meal with you, my goal might be to make the food that I have tastier. And this leads to planned communicative acts. For example, I might think that I'm eating with you, you're near the spices like the salt and pepper. I'm going to ask you for them because they're farther from me, or I would have to reach past you in order to get them. Let's say that's part of the context. Then I choose some words that I would use to communicate. I maybe have to do additional work like figuring out the linear order in which I communicate. And then I turn that into something that goes through a communicative channel, spoken language or signed language, depending on the linguistic context and the language that's shared by the interlocutors. So that's the generative process, okay? And so the errors are going forward from higher level processes to lower level, closer and closer until actual language is produced and carried through a communicative channel to the comprehender. The comprehender's goal is to reverse engineer this process that led to the sounds or the signs that they got in, and they reverse engineer the likely structure and intent of that message, of that signal. And the optimal way of doing this, according to probability theory, is through Bayesian inference. This leads to, for example, for incrementality, two crucial sort of equations. One is in interpretation that we should use Bayesian inference, okay? And Bayesian inference says that given a linguistic input, that the probability distribution over interpretations is proportional to the prior probability that an interpretation will be something that the language producer, the speaker or the writer intended, reconciled with the likelihood of the input given the possible interpretation. And then for incremental prediction, there's the law of total probability. And that says that given possible interpretations of incremental input, T, the predictions of the optimal predictions about the future do what's called marginalizing over possible interpretations. And so that means that ambiguity management, the multiplicity of possible interpretations, is optimally managed by holding them all as possibilities, weighting them by their probability given the past input and the context, and then determining the prediction for each possible interpretation of what's going to come next, and then averaging them out, taking a weighted average. Those are the sort of two fundamental equations. So what this looks like in context, for example, if I'm thinking about the role of syntax and ambiguity in syntax, I might think about our minds scoring possible syntactic structures and then using those to predict. And this does things like when you make this incremental, you take a garden path sentence, like the woman brought the sandwich from the kitchen tripped. And, this is confusing because the words who was in this case, there's a grammatical rule that allows you to omit them. And the ambiguity of the form without who was can be captured in sort of the sizes of these trees, or like the relative probabilities, these probabilities of interpretations given past input. And this continually evolves. And then at this word, which is very hard to interpret, tripped, this is incompatible with the interpretation that was preferred, and it's compatible with an interpretation that was very dispreferred. So that makes this a very surprising word. And it could be one that if you, for example, have computational limitations and aren't able to retain this low probability interpretation, you might completely fail at interpreting, which in practice, that's what people do. So this might be kind of evidence that suggests maybe we do have to revise initial assumptions that we can do perfect marginalization as comprehenders. Maybe we only maintain some interpretations, okay? And this leads to some ideas in rational language processing. I'll discuss the first two today, surprisal, which is the idea that a word's information content, the log of the inverse conditional probability of the word given its context, determines its processing difficulty. Noisy channel processing, that we model production errors, environmental noise, and memory limits. And then the idea that I won't talk about today, but that I just want to allude to, is the idea that actually from an informational point of view, speakers actually utilize compensatory mechanisms to optimize utterances in terms of surprisal and noise. Okay, so I'll just take up the first one. This idea actually is now nearly 25 years old, that the difficulty of a word in terms of the relationship with its context of processing it successfully is quantitatively indexed by the log of an inverse probability. This is known as surprisal or information content. In a way, it's the most basic quantity in classic information theory per Shannon. And this captures, if you say that, one qualitative thing that it does is it captures the expectation intuition. That the more we expect an event, the easier it is to process. Brains are prediction engines. And we've known for many decades that predictable words are read faster, have distinctive brain responses, and so forth. And already for several decades before large language models, we had probabilistic models that we could use to make word-level predictions that capture syntactic structure, and you can get grammatical expectations. But surprisal goes on a little more specifically. So this is the picture between raw probability, which ranges from 0 to 1, and surprisal, which ranges from 0 to infinity. A probability one event carries 0 bits of information. It tells you nothing, but it has to happen. A probability 0 event never happens. If it did, it would be infinitely surprising. And in work now that's over a decade old, we demonstrated the first quantitative relationship between probability and a really independently justifiable measure of processing difficulty, reading times. And the idea is we take reading times in different domains, different kinds of methods, for example, cell-paced reading, which is a more artificial method that's been used for many decades, and eye tracking, which is a more naturalistic method. You just use an infrared camera to monitor eye movements as people read. And we used big data, data sets of 5,000 or 50,000 words to disentangle the relationship between the effects of probability of a word given its context on reading time with other variables that have been known to influence reading, like frequency. And in word language, in data that we first used n-gram models before deep learning was really on the scene in a way that we can use now. And we actually found over many orders of magnitude in probability that this relationship indeed was linear. And this was really quite striking. Okay. However, we're now in the era of large language models. And so to say a little bit about more large language models, I won't go in too much into their internal architecture, but what I want to emphasize is that whatever the internal architecture is, okay, and today, the main architecture seems to be the transformer, in particular the GPT variant of the transformer. This is the classic transformer. The GPT variant is very slightly different. But this is still a pretty good characterization. The internals here look really complicated, but what I want you to pay attention to is that behaviorally, what matters the most, what really matters is ultimately the output probabilities, the next token probability distribution, which you read directly from the output layer. And this is a conditional probability of the type that I just talked about. And so you can directly calculate surprisal values from it. And one thing we've done in work, a line of work that maybe one crucial culmination is Wilcox et al. 2023, is we use it for controlled testing of grammatical knowledge of large language models. And at the time that we started this back in 2018, I will say that and I think many, many people in linguistics were very skeptical that that what are now known as large language models would really be tracking something as deep as sort of subtle aspects of what we consider the fundamental sort of machinery of syntax and grammatical structure in language. But I think the picture has turned out to be very different. Here's one example of how we've done this. Here's a grammatical sentence of English. I know what the lion devoured. And I'm just highlighting two things in this. I know what the lion devoured at sunrise. And I'm highlighting two things in this sentence, the word what, and the lack of an object, a noun phrase on its own after the word devoured. That lack of an object is the underscore, and these things are often called the filler and the gap. Ordinarily, the word devoured has to have an object next to it. This is a property of this particular word in English, a syntactic property. But the word what is what's called a filler. It licenses the word devoured to appear without an object right after it, instead having a gap, the absence of an object. Okay. If I either remove the filler or fill the gap alone in the sentence, I get something ungrammatical. And understanding that relationship between the filler and gap is best understood using the hierarchical structure of language from traditional generative linguistics. So this word what is structurally above the word, the gap, and it exists in a tree structural configurational relationship that licenses the gap in that position. And I'm sketching that relationship here. I'll call that the filler plus gap version of this sentence. If I remove the filler, I change the word what to that. In this case, the sentence becomes ungrammatical. I know that the lion devoured at sunrise sounds terrible to any native English speaker. I know what the lion devoured the gazelle at sunrise has the filler, but it doesn't have a gap. That also is ungrammatical. But if I remove the filler and fill the gap at the same time, it's fine. I know that the lion devoured the gazelle at sunrise. So this is, from this perspective, this is what's called a 2x2 interactive design, factorial design in experimental psychology. And these kinds of controlled designs help us get at the kinds of ways in which probabilistic models of language, and language LLMs in particular, can and do learn grammatical patterns. Okay, there is, from a theoretical point of view in linguistic theory, there is signature central theory of a feature of natural language grammar. So let me just give you an example using a different pair, but it's the same configuration of the surprisal by word surprisal profiles of these kinds of sentences. So we'll first focus on the first pair where there is there is no gap. Okay, so here I have in the context either the word that was there, or there's no filler, or there is a filler. And what you can see is that when you get to the gap, when you get to the place where you might have a gap, but you don't, the model is more surprised when there was a filler than when there was no filler. Okay, so that suggests that that's one piece of evidence suggesting that the model expects a gap at that location. It's not complete evidence, but it's one piece of evidence. And this, it turns out, empirically matches a classic pattern known to exist in reading times. That it's called the filled gap effect. When you expect a gap and you don't get one, then you're surprised and reading times are inflated. Now let's look at the other version where there is a gap. Okay? Where there is a gap. In this case, these two sentences, obviously we can't look at the surprisal of the gap because there's nothing there. So what do? We look instead at the surprisal of the next word. In this case, it's the word to. And in this case, what you see is that the pattern is reversed from the left panel. Here, the model is more surprised at the word to when there was a filler, when there was no filler, than when there was a filler. So the filler facilitates the event that would ordinarily be surprising, which is, it facilitates the lack of an object. Okay, so that's sort of this reversal pattern. It's a flip in the relative surprisals. Now, if I take the different scores of the surprisal, word by word or region by region, in each graph, and now I'm going to represent them as a single line where 0 would be the same surprisal with or without the filler, I get this following interaction pattern, which illustrates the interaction. You can see that really that what doesn't matter earlier on, but when you get to either the object itself or the filler, if there were no the immediate next word, if there were no object, then you see an interactive pattern. Okay, so you're more surprised if there was no filler than if there was a filler than if there was no filler at the object. And if there is no object, you're less surprised at the next word if there was a filler than if there were no filler. So we call that the WH effect. And this pattern I'm going to have it, red lines are higher, red lines should be above 0, red should be above 0 here, and blue should be below 0 here. That's the signature pattern that I'm going to use as a shorthand for the next slides in illustrating what it is to have a filler gap dependency captured probabilistically in the statistics of a language model. And what we find is that now these are actually relatively old models, but they're still good ones to use, that for a variety of large language models and even small language models. So this is a model from 2018 using an LSTM architecture that is trained on only 100 million words. Even with that model, you get a robust filler gap dependency. And this is across different locations of the gap and the subject position and the object position inside a prepositional phrase across models. There are many, many other things that I could tell you about this. I want to point you to syntaxgym.org, where we have summarized a lot of these kinds of tests and actually use them to quantify performance of models. And there are many, many other things to see in these papers. But of course, now I'm going to get back to these days, if you look at a commercial LLM like ChatGPT or Claude, the next token probabilities are not available to the user in the classic one. So, and you get these and then you also have other things that they're throwing on top of just next word prediction training, like reinforcement learning with human feedback and so forth, that really obscure what the models are actually doing. And Yoav Goldberg here, has a very clever thing where he asks ChatGPT, what are probable candidates for the next word of the sentence? The dog barked because, and ChatGPT says, I can't do that. And it's very ironic because actually the only thing that ChatGPT can do is actually predict next words of sentences, but it won't fess up to the fact that it can do it. And that just tells you the relationship between what the models are actually doing and what they talk about. Okay, so this is so for next word prediction, of course, we call what we might call the direct way method of next word prediction in print, like under the hood. What the models are doing is they're putting a distribution using a neural network given the context over next tokens. But actually, increasingly you're seeing people resort to what we call metalinguistic tests of language models' grammatical capabilities by actually creating a prompt that actually queries the language model in natural language. What word's most likely to come next, for example, for next word prediction. So we'll call that metalinguistic. And one big question is actually, how similar are these behaviors and which ones are better? Like, is it better? Are the models better with the direct methods or with metalinguistic methods? For sentence judgments, this might be probability comparison versus asking the model, here are two sentences, which is a better English sentence, and so forth. So we have different, in Hu and Levy 2023, we have different ways of testing LLMs this way, word prediction, semantic plausibility, and syntax. And what we find, I'll summarize, this is a whole complex set of results, but I'll summarize it as follows. In all of the graphs, including this one where the numbers are all below 0 because they're log probabilities, higher numbers are better. So bars that are higher up are better. And the darkest bars are the direct method. And basically in pretty much all cases, the direct method is better than metalinguistic methods, except in a couple of cases where the metalinguistics methods are sort of on par. Okay. And so this is a very wide-ranging result. And this really matters for conclusions about whether large language models really are capturing grammatical knowledge or not. So for example, Dentella et al. Had a pretty high-profile article in 2023 where they did what we would call metalinguistic evaluation of large language model grammaticality judgments. They used prompts which were, is the following sentence grammatically correct in English? And then they would show the sentence. These are kinds of example sentences. So you have center embedding, weird adjective order, sorry, this is negative polarity items. This is adjective order. This is center embedding. All of these are actually fine. You'll find that it's obvious that these first two sentences feel fine. This sentence is hard for the reasons that I described, for memory limitation reasons. And the ungrammatical versions of these three are here. All of these will feel weird to you. Okay.
Do you think you're showing your pointer?
Yeah, do you not see the green? I have like little green stuff on the slides.
Right, yeah, but when you're saying this and this and this, that, okay, I see.
Okay, great. Thanks. Yeah. So, and what they found is that there was a really big yes bias. So in general, the models tended to say that GPT-3 said tended to say yes, things are grammatical. And that actually made them below chance on a lot of these evaluations for the ungrammatical sentences. And they were actually pretty near chance overall when you average between grammatical and ungrammatical. So it looks like the models are actually really bad at capturing grammaticality information. However, we reanalyzed their materials using the direct probability measurement, where we would just take minimal pair versions of grammatical and ungrammatical sentences and ask in what cases do the models actually put higher probability on the grammatical sentences than on their ungrammatical correlated minimal pair. And it turned out that they were incredibly good at all of these same materials, with one big exception: center embedding. And an interesting thing about center embedding is that in center embedding, because of the way we construct the minimal pairs, the ungrammatical sentences are shorter than the grammatical sentences. So there does seem to be sort of a bias, which is something that I'm going to get to in a second, for these models to put higher probability on shorter sentences than on longer sentences above and beyond grammaticality, a tendency to put higher probability on grammatical sentences than ungrammatical sentences. So, but when you do good minimal pair comparison, for the most part, models are really good at putting higher probability on grammatical sentences than on their corresponding minimal pairs. And we can go even farther. We can take those same materials and we can use but one of the really neat things about this data set that Dentella et al. Used was they also collected human judgments, many human judgments per sentence for their materials. And they found, first of all, that the humans were very good at distinguishing grammatical from ungrammatical sentences, with the exception, once again, of center embedding, which are these blue X's here that you can see, where humans are really not that great. Okay, they're actually close to 50-50. Okay. And they're actually they're not good at distinguishing grammatical from ungrammatical center embeddings. This is actually a well-known phenomenon in psycholinguistics. If you actually if you take a sentence and its minimal pair, so you have one grammatical and one ungrammatical sentence, you compute the surprisals of the two sentences, and then you take the difference between those two and the surprisals of those two sentences. And you plot that on the x-axis as the surprisal difference between the sentence and its minimal pair. And then you look at the rate of human acceptance of the sentence. There's a very strong correlation between those two things. So actually, not only is there a qualitative capturing of grammatical sentences are higher probability than ungrammatical sentences, but actually fine-grained variation in human judgments is explained by the magnitude of the difference in log probabilities between the grammatical and ungrammatical variants of the sentence. Okay, so that's really neat. It seems like the language models are doing a great job of capturing grammaticality patterns using probabilities. So it's like probability seems to be capturing what in a traditional linguistic theory would be described as grammaticality, or the ability to assign a structural description to a sequence of words. However, there are puzzles that really remain. So for example, here's a data set that is maybe the most widely used data set of minimal pairs in evaluating models for grammaticality judgments. This is called BLIMP from Worstad et al. 2020, and they look at many different kinds of phenomena. And I'm just illustrating to you here examples from their paper of minimal pairs. So for example, many girls insulted themselves, grammatical. Many girls insulted herself, ungrammatical, because there's a number mismatch, and so forth. Okay, many different examples. Okay, so if I use, say, log probabilities or variance of log probabilities, and I ask how well in the BLIMP data set do LLMs, say GPT-2, which is now an old LLM, or Llama 3, which is a fairly recent and much more performant LLM, how well like how often do these models assign a higher probability to the acceptable version of the grammatical version of the sentence than to the unacceptable minimal pair? And the models are always around 80%. Interestingly, by the way, you can see Llama is actually not better than GPT-2 on minimal pairs. Very interesting. Okay. So all of that improvement, all of that, it seems that actually like you didn't need to get to Llama 3. The more recent generations of LLMs, actually already with GPT-2 in 2019, you were capturing these broad grammatical facts about English. Okay. However, I'm going to now say, let's pool all of the materials, all of the grammatical sentences and all of the ungrammatical sentences. And now I want to look at the distributions of log probabilities of each group. And if I do this, it turns out that the two distributions are almost entirely overlapping. This is for GPT-2. Okay. And so for this kind of thing, there's a natural question which arises, which is, so how well does log probability separate the pool of grammatical sentences from the pool of ungrammatical sentences? And you can see it's going to be obvious that it is very bad. So the question is like, in general, how well, when I draw a line saying all the grammatical sentences should be on the right side, higher log probability, and all the ungrammatical sentences should be on the left side, lower probability, how well is that happening? And the quantity that's used for doing that is what's called the area under the curve. And an area under the curve of 0.5 is not at all, and an area under the curve of 1 is perfectly. The area under the curve for both GPT-2 and Llama, using all of these different variants over here, both raw log probability and its log probability and their variance, is very poor. Okay, so it's not much above 50%. So we have this apparent paradox between performance on minimal pairs and performance in separation of pooled probabilities. And what this gets at is that really at the end of the day, it really isn't the case that probability completely captures grammaticality in large language models. Rather, if you have well-controlled pairs of sentences that are mostly the same, but differ only in grammaticality and differ in a particular way, then the models are really good at distinguishing which is the grammatical version. Okay, but that's fair. It's still very different. And this is just in the direct probability measurement method. Still very different than what humans are doing. So I'm really excited about some recent work that we've done, which tries to theorize this, how LLMs are capturing linguistic knowledge. And the theory goes in some as follows. Like underlyingly that models, and frankly humans as well, there are messages we want to convey, and those get mapped to different possible strings. Okay, so for example, string 1 might express a single moon. A single specific moon is emerging, the moon. That is expressed by the string the moon emerges. Meaning 2 is expressed as a moon emerges, and meaning 3 is the moons emerge. Okay, those are all grammatical strings. In the neighborhood, in some relevant sense of neighborhood, of these grammatical sentences are other sentences, other strings that actually do not grammatically encode any meaning. So, and the idea is that that in corpora and as a result, in a noisier way by large language models, strings get probability by either grammatically expressing meanings or being close to expressing meanings that are likely to be conveyed. And for the human, for the corpus, the ones that are ungrammatical but are still occur in the corpus come because there are errors. And in the LLM, the ones that are ungrammatical but still get probability is either because they were in the corpus as errors, or they're sort of in the generalization neighborhood of the strings that occurred in the corpus. So you get sort of this pattern where you can see there's a tendency for but it's not perfect for the ungrammatical strings to have higher surprisal than the grammatical strings, but all of them get some surprise. And so you can see that the model, even in this small set that is usually represented on a cube of sort of 3 different kinds of edits, you don't have perfect separation. So that's the idea. So, and this actually helps us. It actually helps us understand this. So it says that when you pool sentences, you're sort of confounding two things. There's the message probability, right? So some messages are just way lower probability than other messages. And then there's the probability of successfully expressing the message without that message, or and if not, then what do you express it as instead? And that second term is sort of like how noisy are the LLMs in mapping messages into, even though the messages themselves are not explicitly represented in the models, how successful are they at keeping their probability mass on grammatical strings? And there's this noise term, but sometimes the noise term is dwarfed by the message probability term. Okay, and so there you that is that the noise term is in a sense the sort of systematic offset between the two distributions, but the range in message probabilities is the spread within each distribution. And though that latter term is vastly varying, and that helps reconcile on the one hand the upper results that we see here and the lower results that we see, both the high performance on the bottom and the range in probabilities on the top. Okay, so I only have a few minutes left, and I want to make sure there's ample time for questions. So I'm actually gonna just skip ahead and just show a couple of things, and then illustrate one other thing that's really quite two other things very briefly. So one is we've used LLMs as well, and additionally new large data sets, both within English, many different data sets within English, and many different models within English, to revisit the quantitative relationship between surprisal and reading times. And it turns out that broadly speaking, aside from say like there are a couple of exceptions, but generally speaking, this linear or near linear relationship holds between surprisal and reading time in English, and indeed across many languages. So in all 11 of the languages that we've looked at in an 11 language study by a different Wilcox et al. To a 2023 paper, we see over orders of magnitude, over many ranges of bits of surprisal, this relationship is linear or extremely near linear. And even with the exception of Hebrew, which we don't really understand why there's an exception, not only the fact that it's linear is similar, but the milliseconds per bit measure in eye movements and reading is very similar as well. That is, the slopes are very similar. So it almost seems like we're capturing some kind of invariant that studying eye movements and reading is quantitatively picking up in how information gets processed and manifested in terms of contextual probability and reading behavior. Okay, and that's incredibly powerful. Both theoretically, it has a lot of consequences, but it has methodological consequences. So we can do things like talk about milliseconds per bit or per band. And so, for example, Quanjung Huang in work with Tao Linzhen and Brian Dillon has done interesting work showing that, like, actually, if you go back to severe grammaticality violations, you actually find that although in naturalistic reading, this relationship is really a good predictor, it actually can really badly underpredict the amount, the quantity of processing effort as measured by reading times that one experiences when you have grammatical violations. And in work out of our lab, we've also shown this. So for example, going back to these filler gap dependency results, in red is cases where there's a what we would call a grammatical expectation violation. Sometimes that's a true ungrammaticality. Sometimes it's just a grammatical expectation violation and the sentence is grammatical in the end. Those are the red dots, and the blue dots in this matrix are ones where there's no grammatical expectation violation. And you can see that the prediction error of our model calibrating surprisal to processing time is generally quite small when there's no expectation violation, but it gets quite bad when there is an expectation violation. So this quantitative model of surprisal from an LLM to processing difficulty actually allows us to reveal possible discrepancies between what an LLM is doing and a human is doing. And one reasonable hypothesis for those discrepancies is that humans are actually using symbolic mechanisms that are causally implicated in processing processing difficulty in a way that LLMs don't. So it's actually revealing a real difference in processing between LLMs and humans, which is of great theoretical interest. Okay, finally, I just want to say a little bit about noisy channel language processing. In gray, I sort of have the classic. So this is the classic Shannon picture of noisy channel language processing, sorry, of the noisy channel. You have an information source here. It encodes a message in a transmitter, sends it through a noisy channel, and is received and then decoded at the destination. And success happens is when you recover at the end the message that was intended at the beginning. And in blue and in black at the bottom is my sort of glossing of this Shannon diagram in terms of language processing mechanisms. Okay, a speaker intends something, they have production mechanisms that lead to an utterance that is transmitted across a noisy channel. Input and memory mechanisms lead to further noise, and you get basically an input, and you have to, you get the utterance and that reaches the noisified utterance that reaches the receiver. I is the input to language comprehension after input and memory noise terms. And then the goal is to actually recover probabilistically the message and the utterance that were intended. Okay. And in the real world, actually, it's amazing what noisy channel mechanisms can do. So Sarah Palin, for example, was famous. This is now old, classic politics, but she was a Republican vice presidential candidate in 2008 in the U.S. And she had examples like, she would say, "I'm not going to solely blame all of man's activities on climate changes and climate." It's obvious what she means. It's actually hard to notice that she made a grammatical error, but she did. It should be blame all changes in climate on man's activity, on man's activities. Likewise, I'm not one. She did this over and over again. I'm not one to attribute every activity of man to climate change. This was so common that it became a joke, a running joke in the media about her malapropisms, but nobody ever misunderstood it. Okay, and just to briefly describe sort of a pattern of this that we see in incremental processing. So I'm going to go back to center embedding. So here's a difficulty gradient. So the report was surprising, not hard. The report that the doctor annoyed the patient was surprising, a little bit hard, but not too bad. The report that the doctor who the lawyer distrusted annoyed the patient was surprising, very hard to understand. And the understanding difficulty, it seems to be really here, right? So this is totally fine. This was at the top, number 1, totally easy, was number 2, harder, was number 3, really, really jarring. And interestingly, like some counterintuitively, perhaps, one minimal change to the sentence. For example, if I change the word report to the word fact, the fact that the doctor who the lawyer distrusted annoyed the patient was surprising. This actually becomes much easier. Okay, why the difference? Intuitively, here's our sort of idea that report is usually not followed by a relative clause, a complement clause. The report that the doctor annoyed the patient, that's not usually. Report is followed by something like the report by the doctor or the report about the doctor. Okay, so in some sense, in the neighborhood of the true, at this point where the word was might appear, where the true sentence, this could have the word was next. In neighbors of the context, like the report by the doctor annoyed the patient, where the word that, it's one change, that gets changed to by. Now the word was cannot occur next. Likewise, if it change that to about, okay? And in a sense, these variants, these are actually maybe real competitors with the true context, because the word that is not this phrase is not a particularly common kind of structure to occur after report, but it's a very common kind of structure to occur after fact. So relatively speaking, these variant contexts, these competitor contexts, they're not good competitors in the same way that these are good competitors for this context. That's the conceptual idea, okay? And so we actually have built an at-scale noisy channel processing model that captures this, okay? And so just oversimplifying a little bit, schematically, the predictions that we want to have are as follows, that the simplest versions where there's no embedding, as the embedding bias goes up, like the word fact is over here on the right, and the over here on the left would be the word report, that the word was gets a little harder to process, because you expect, if the embedding bias is high, you expect an embedding. Not getting embedding is surprising, but if there is an embedding, then that word was after the embedding. The higher the embedding bias it is, the less surprising and less difficult that word gets, because your representation of the context improves. Okay, and there's a secondary effect, which is that if I change the word annoyed to the word cured, which makes it clear who's doing what to whom, then that also makes things easier. Okay. It turns out that surprisal on its own conceptually gives us a very different picture, where these green and blue lines are flat. And in fact, actually, that is what you see in large language models, even going back to GPT-2. You don't really see the right pattern. And we have a model where we say, okay, this is a case where actually LLMs, even GPT-2, and even more so the more recent LLMs, they're behaving in a way that's superhuman in a theoretically interesting sense. They seem to be using the context more effectively than humans do. Okay, and so how do we model what humans are doing? That is the human limitations on processing. So what we do is we say, actually, maybe what humans are using as context is not the true context, but a noisified version, one that has been passed through a noisy channel of memory from the past. And so we give it a lossy representation, and we model that by saying stochastically certain words might just get erased. That is, you forgot the mind has forgotten what they might be. And then the overall architecture says, given those noisy versions of the context, use Bayesian inference to try to figure out what the context might actually have been. And sometimes it'll be the true context, like here, but sometimes it'll be these other contexts, like here. And so then we use the law of total probability that I described earlier, and we get next word prediction. Here's the law of total probability. And then this model is optimized. We have free parameters, which are retention probabilities in this model, which model the nature of memory limitations in language processing, noise in the mind. Okay, and we optimize it for good next word prediction in the context of noise. And then it turns out that that we actually get these predictions. Sorry, I should jump to the here's the main results. So we have two experiments where we have human behavioral data. So our theoretical predictions, you can see blue and green go down with embedding bias going up. Green is below blue. Red goes up instead as embedding bias goes up. As I said before, surprisal theory doesn't really give us this very well, but our model gives us this very well. Okay, so when we actually noisify GPT-2 on the basis by making its retention probabilities worse, we also get similar and more nuanced results for an experiment that also manipulates the verb semantics. Okay, and we even see this in language production, where basically we have a conceptual prediction that people are worse at completing these partial sentences. Like these examples that I showed you that language models do incredibly well on, people are worse at those when the embedding bias is low and better at them when the embedding bias is high. Okay, I'm a little over time, so I want to just wrap up now. Okay, so hopefully what you've seen here, let me find my summary slide. Where did my summary slide go? Okay, so hopefully I've shown you that LLMs actually fit beautifully within this broader concept cognitive science agenda of rational analysis. They help us test theories in computational psycholinguistics flexibly and at scale. And when they systematically fail, be it fail at their own behavior, fail at actually processing in a human-like way, like assigning higher probability to a short ungrammatical sentence than to a long grammatical sentence, or to have superhuman processing behavior in things like center embedding. They actually offer opportunity for further insights into human cognitive constraints and mechanisms of grammatical knowledge. So these technologies, together with open data and analysis techniques, make it a hugely exciting time for language science. And I want to thank, of course, funders, my laboratory, my collaborators, and all of you, especially for listening. And I'm happy to take questions for maybe 15 minutes or so.
And so we'll first thank you for your comments. Now, normally at this point in the talk, you have the luxury of, if Roger had been this faithful to the timing, you would have a half an hour left to ask questions. But now we have much less.
Well, let's say we have 20 minutes.
20 minutes. And usually you take a while to warm up to questions. I want you to warm up faster.
I will. That's fine. I do. Yeah. So Ask away.
This is for them.
Oh, I see. Got it.
Don't wait. Okay, Nick, go ahead.
Hello, hi Stephen, hi Roger.
Hi.
Very nice to see you. I just wanted to ask about sort of connected two bits of the talk. You mentioned the fact that humans are very good at dealing with words that are mangled, sort of jumbled letters. And from a surprisal point of view, you might think that was quite strange because you don't see too many of those in real text, and yet we seem to adapt them very easily. And I wonder how that works. I mean, I presume there's some kind of levels of representation thing going on there. But I mean, if I were doing a reading time experiment with one of those slightly mangled sentences, presumably I'd be quite quick, I'm guessing.
Yeah.
And yeah, it's really kind of, in a sense, objectively, it's like a really low probability stimulus. But presumably, I'm assuming this is somehow a matter of which level of representation you're worrying about.
It's a really great question. I actually think there's a really clear answer to it. So let me get the right slide.
Brilliant.
Yeah, I think there's actually a really, really clear answer to it. Okay, so here's the slide, the noisy channel language processing theory slide. Okay, so this is where okay, where does noise happen? I think the right thing to say is that it sort of happens here. Okay, so this is where it can happen, and I think it's useful to distinguish three key sources of noise. Okay, so one is here, sort of in this space, which is I'll call it speaker error. Okay, so that is, or it's maybe like here. Let's put it here. Okay, that's where the relationship between the intended message and the utterance that was actually produced, which is sort of the starting point of the signal, is not faithful to the form meaning mapping determined by the grammatical facts of the language that the speaker knows. So that's source of error one. Okay, source of error two is, I'll call it here, which is in the environment. Okay, so that's things like the ambient noise in the room, dimness of the screen, and so forth. There's a third source of noise here, which I think is underappreciated a lot, and that is the constraints that once the signal hits the comprehender. So if it's auditory input, it's like, you know, the like hearing systems in the ear, but also things that happen farther in, which are harder for us to know exactly what's going on. But things like memory constraints, the fact that, because we're, of course, as you've eloquently described in much of your work, language involves integration of information over time as it comes in. And so the past is not perfectly represented. And so memory constraint itself is a source of noise. But here, I think actually, when you go to the scrambled letters, I think what's going on is that actually the input mechanisms are actually a major source of constraint. And actually, interestingly, and one of the constraints is there's actually this rich literature that sort of goes outward from psycholinguistics into other aspects of like visual processing on like, you know, how does recognition work, visual recognition work? And, you know, I think the general theory is actually you're decomposing the image into these little pieces and actually reassembling it. And actually that decomposition, like all the detailed facts, many of the detailed facts of like linear ordering, for example, relative linear ordering of smaller units may be lost, you know, or poorly represented. So actually, when you go to one of these, when you go and you ask, what is the linguistic experience with something, you know, what linguistic experience do we have with this, with things like that? It actually might be much more than you might think. Because actually, a word like according is actually not faithfully represented when it gets into language processing mechanisms by a really high fidelity linear ordering of the letters. And so there actually we might have much more experience than just our recording of the linguistic environment outside of the mind suggests. That is my speculation. And I actually think that the broader literature is actually very consistent with that.
Yeah, no, I think that's pretty convincing to me. Thank you.
Yeah, great question.
Okay, next question, or else I'm going to jump in. Just to not waste the time. We've had, just raise your hand as soon as you want to ask a question and I'll shut up. I don't want there to be silence now. Not everybody is deeply involved in the subtle and profound details of all of this, like Nick. So I'm going to ask a question, and I'm not. I'm going to ask a question that's closer to what's in more people's minds right now, which is this business about the cases where the human profile, probability profile, and the LLM profile is different.
Yeah.
And what light that casts on where it isn't different.
Yeah.
Because there's prima facie, what they're doing is so different in every way from what we're doing. What is responsible for the overlap? Is it because we're in a super? Well, anyway, I don't want to fill it in.
That's a great question. Yeah. So I have lots to say about that, but actually, let me ask you a question back to start. So you said prima facie, prima facie, the what they're doing is so different from what we're doing. Is that really true? Like, to what extent is that true? And when in these cases where I'm presenting, let's say using text, I'm presenting a textual input that bears no systematic relationship to the broader context in a way that is often the case, right? So it's like you're reading a snippet of a book. You like turn a book to a random page, read the first sentence. So is that really how do you know? I mean, I believe that it's really different, but I wouldn't say it's prima facie. I would say that that's actually a conclusion that we have to draw empirically. Because the broader mechanism, obviously there's some differences between specific LLM transformer mechanisms and what we're doing in the mind. Sure, we don't have time for as many layers of processing as they use, but some of the general motifs, distributed representation, sort of query, key query match, some of the broad mechanisms of the transformer, they might not be that different from what's going on in the mind.
Well, I'm going to stick to what I said.
Yeah.
2 hands up, and so I won't pursue it.
Yeah. Okay, sure.
First,
okay, but let me actually give you the answer in terms of like, what does it tell us? I actually think this is an extremely rich source. Like this being able to say at a quantitative level that, first of all, you can see that in some cases, actually, there is a good quantitative match between the predictions of the models on a case-by-case basis and human reading time behaviors. You see those in blue, right? And then there are these other cases where there's a bad quantitative match. And in particular, the models seem to underpredict the difficulty as measured by reading time. This is extremely productive to observe. So for example, some cases, for example, I don't actually have them here, but for example, like Quanjung Huang's work, which I showed on the previous slide, that was about ambiguity resolution for the most part, like garden pathing. Okay. So they found like garden path ambiguity resolution, when you have a structural ambiguity and it resolves to the low probability structure, it's hard. It's especially hard. And there's one class there's a natural class of theories that you can use, which is like, it's like I said, you didn't maintain all the possible interpretations. You may have discarded some, and so you're at a loss when you get something that just doesn't fit with the current interpretation.
Okay, for your sake, I'm going to invoke closure so you get more.
Wait, but I do want to say one other thing, but we can actually go even beyond that, which is that these are cases where there was no ambiguity from a natural, like what many psycholinguists would not say there was ambiguity before you hit the hard thing here. Like here, it's the word the slides. What was the ambiguity here, right? So that tells us something else, that there are maybe there's a privileging of structural expectation. Then this gets, this might be an interesting connection all the way back to like the work of Fodor on modularity of mind, a source of evidence for like some truth to what he was saying that in a very different way than you might have anticipated getting. Anyway, I'll just close that out to make sure there's time for the questions.
Okay, next question is
very theoretically productive.
Next question is from Steve Hansen, and he's not at Rutgers now. He's in Aberdeen.
Great.
Yes, hi. I am in Scotland right now. Yeah, it was a lovely talk for a number of reasons. One, I love the alignment and the subtlety that your work shows with regard to syntax and what is happening within the LLM. Now, at some point, this breaks down for me a little bit because the log surprisal, which, is a very old term used in chemistry and physics, it's used all over. But you're using it in a kind of a special way. And I believe you showed, correct me if I'm wrong, that there's this linear relation with reading metrics, duration, or time span.
Mhm.
Now, but now we have these GPTs, and although we know how they learn, we use some, log negative entropy or something to train them. We're not just gradient descent as back propagation, really. What does that, how do you reconcile this surprisal measure, which I think you're right, is very important, with the fact that GPTs are doing something completely, kind of normative mathematical statistics? There's very little evidence to show that their training algorithm has much to do with the contextual structure that they're learning internally, or much to do with these alignment. That is, I don't see a lot of studies with alignment where they've done careful parametric analysis of the kind of training. So I almost wonder, should GPT be trained with some kind of surprisal metric?
No, it is. It's a great question. And it is. It is actually. So actually, this is a great point to look at rational analysis and say, so this is the recipe for rational analysis. And, I talked about applying it to humans, but actually, no, surprisal. So cross entropy is the measure that LLMs are being optimized for in what's called the pre-training stage, right? So that's where you just train them on next word prediction. It's cross entropy that they are
right, a negative log loss. That's right.
Right, exactly. Yeah, and so that actually is that is basically it's an average surprisal. It's the same thing as average surprisal. So they're
is it?
Yeah,
is it? I'm not so sure.
No, it is. It is definitely the same thing. Yeah, we can.
Okay.
I'm happy to take that offline, but it's definitely the same thing.
I think we should take that off.
Let's take it offline.
But I do. There's variations in these trainings. So you're focusing on surprisal as being a key element here in linguistic emergence, I think, if I understand what you're saying. And I don't see why that's directly connected to a GPT, but maybe I'm wrong.
Okay. Yeah, but I do want to say one more thing about the relationship with humans. But I think it's actually much easier to show that, if you do a rational analysis, let's put it this way. Let's apply rational analysis really fast to the LLMs. Okay. So their loss. So trust me for the moment that actually their loss function is equivalent to minimizing average surprisal. That they then, so they need to learn the statistics of the environment in order to the linguistic environment to do that. And in order, the statistics of the linguistic environment reflects grammar and syntax and all that. So they're learning those things in order to do what they're supposed to do well. Now, the other question is so why would you see that linear relationship between processing time and surprisal in humans? Why would humans care about probabilities of next words? You could say, sure, it's important for me to predict interpretations given inputs, but why do I care about probabilities of next words? I think there are a couple of things to say about that. One is there are theoretical reasons in terms of the time surprisal relationship. There are a number of ways of theoretically deriving that relationship, and I can point you to references later on. The other thing I'll say is that for noisy channel correction, it is actually important to be able to figure out exactly what somebody intended, or to identify your own language production errors. And deploying probabilities at the input level is really important for that. So those are reasons why getting probabilities right for a human would be important. So that's where they're going to dovetail, because even if they're somewhat different architectures, maybe very, very different architectures, they actually there's an important sense in which the objective function is aligned between the humans and the machines.
Okay, we have to move to the next question.
Thanks.
Yeah.
Okay, we have to move to the next question. I also want to say that there were lots of questions submitted by the local doctoral.
I did see that, and I'd love to get a couple of those.
Yeah, but we don't have time.
Well, I'm happy to take. Maybe I can take Kevin's question and just take a couple of minutes to comment. You mean the written ones, right?
Yeah,
I'm happy to go over a couple of those.
Okay, but they were sent to Roger, and they were translated into English where they weren't in English. So the Roger's got them all, and he liked them. So he'll get. Okay, Kevin, have a go. Don't disappear.
Okay, I think I have not disappeared.
Hi, great to see you, Kevin.
Yeah, you too, Roger. And thanks for this fantastic presentation. So you made a very strong argument for some high-level similarities and similarities in details between patterns of processing between people and the LLMs. I was fascinated by your response to Stephen Harned's initial question, because you seem to react quite negatively to his statement about there being critical differences, that some fundamental dissimilarities between what people are doing and what LLMs are doing. And yet in your presentation, you had several sort of, very brief offhand comments about, there being in fact critical differences, right? And in fact, at one point you said that, this is obviously not really what people are doing, and that there's an important role for symbolic processing in the minds of people that is not present in the LLMs. And so I just wanted to ask you to unpack, what you consider to be, the strongest evidence for there still being some fundamental differences.
Great, that's a great question. I want to be very clear. What I was objecting to was the prima facie piece. That
Okay.
It's like without looking at evidence, of course, these seem really different. These are really different. And that's true. It's true for like the fact that like we ordinarily process language in a much more sort of multimodally contextualized way than LLMs are doing. I think that is prima facie. But in terms of how we process language without other correlated contextual information, which is a lot of what we're working on here empirically, I just think the prima facie case is not. I think that I certainly came into looking at LLMs with the bias from my linguistics training that these are, we're obviously doing things that are ubiquitously fundamentally symbolic. But I think it's a little different to say and I continue to think that's true. What I think is not clear is whether LLMs are not doing things that are fundamentally symbolic. They may just be doing it implicitly, So obviously we have neurons that are doing these things, and it has to be implicit in what the neurons are doing. And so the question is, it's sort of are LLMs you might think of as the brain, and then what is the mind? Then, that might actually be something much more symbolic in the same way that our brains are neural and, our minds are maybe more symbolic. But I do think, what we've seen empirically is that there are these clear points of departure. And interestingly, I will say early on in my career, when I first started working on surprisal, one of the theoretically really interesting features that I always considered it to have is what I call representation neutrality. So all the predictions of the theory bottom out in predictions of what are the predictions that come based on the probabilities of strings. So the only role of grammar and grammatical structure is inducing probabilities on strings. Okay, so that I sort of came into studying LLMs and human processing once we have LLMs, using that as a null hypothesis. And I think we're now in a position to on the basis of quantitative comparisons, reject that null hypothesis in these cases that I've shown, and that Tal Linzen deserves a lot of credit for showing these in some of the first cases here, Tal and his collaborators. But now we've made, with the help of LLMs, we have these big strides toward a quantitative science of language processing in a way that we didn't have before, and that helps us. Now we can say, look, there's a strong case for these symbolic mechanisms being causally implicated directly in human processing in a way that LLMs don't seem to have. Now, we don't know exactly the nature of that causal implication, but the fact that that's probably it's a much stronger case than I think it used to be. And so the only objection was really the prima facie. Now, I think that we're actually able to build a body of theory that actually enrich, lay bare, highlight, illuminate these differences between the humans and the machines in a way that we weren't able to do without the LLMs and these comparisons.
It's my duty to protect you from yourself.
Yeah, it's cool. Let me just do a couple of quick questions. I really do want to honor the great questions that the students mentioned. So I'll just read a few of them here that I really, really like. So one that I really like is this is a really big one. Could we eventually create an LLM with near perfect accuracy, 99%, that can act and process information like the human brain while recognizing the brain zone's limitation in knowledge? And I think The answer is no and yes. No, yes, and no. I'll put it this way. Can we create an LLM with near perfect accuracy 99%? If by accuracy we mean near perfect accuracy in predicting the next word, no. Language is higher entropy than that. Language is intrinsically unpredictable in terms of what people are going to say. However, I think we can continue to make great strides in creating models that act and process information like the human brain while recognizing the brain's own limitation. So for example, the resource rational model where we create noisy versions of the context is one stride toward that. Optimizing LLMs on their own in the way that industry is doing, for example, I don't think is going to get us there, but I think we can do that. However, I also think that and then this is where, so that was the no and the yes. And the additional no is that I think at the end of the day, my prediction is that we will see that this transformer architecture is just not the right sort of ultimate architecture for modeling the mind and brain. Another question I really love. Do memory differences across languages extend to other domains? So for example, oh, sorry, that's not the one. That's do cross-linguistic differences in the ease of processing verb final structures depend solely on familiarity? For example, would a learner of German find verb final sentences easier in German, in English, than an English speaker with no knowledge of German? Or would an English speaker who's simply familiar with the structure also be an advantage? I think there are these really cool papers. The first one was by Shravan Vasish in Potsdam, and it's from 2010. And he and then Stefan Frank later on showed some really cool things. In particular, they showed that, first of all, you can take these same structures and you can do these verb final complex nested dependencies in English and in German. And they're hard, like there's what's called this sort of the missing verb grammaticality hallucination, where you take out a verb in an English structure and it feels more grammatical. It feels better than if you had it in a grammatical form. So the ungrammatical sentence is more acceptable than the grammatical sentence. That doesn't happen in German, and they have really nice, tightly controlled experiments that show that. But the other thing that's really cool is that subsequent studies did this on bilinguals, German English, Dutch English, and they found that in these bilinguals, who are very highly fluent in English, they behave like the native German speakers when they're doing German, when they're processing German, and the native English speakers when they're processing English. So they had the native English speaker pattern in grammaticality effect when they were doing English. And so it actually seems to track more with the statistics of the environment for proficient, native and even proficient comprehenders than it does with sort of some more fundamental working memory capacity. I will take one last question before I go, and I'm sorry not to be able to stay longer. So so this is a very important one. Without access to log probabilities, what simple and reliable protocol would you recommend for evaluating an LLM's competence? I understand that to be grammatical competence, using only prompting. And how can we ensure that such a protocol does not itself introduce performance artifacts? I would just strongly dissuade us from doing that. And the reason is that we don't know what other features of the training data are required in order for a model, for an LLM, to be able to perform metalinguistically at all in terms of evaluating the grammaticality of sentences. We just don't know what needs to be in the training data. It's clear that on the internet, there's a massive amount of information in English about the grammar of English. It's just there in the training data, right? There's we don't know how, I don't know of any broad cross-linguistic studies of the metalinguistic performance of models across languages with different levels of resources, not even just different amounts of training data, but different proportions of like grammar pedagogy in the training data. We don't know anything about this. So I would just be very reluctant to rely on these at all. And furthermore, I think unless you're talking about very applied reasons, like I want to build like a grammar correction bot, and I'm going to use an LLM for it. Like, that's a very applied purpose. For those purposes, fine. But otherwise, why do you care? You know, like it's not theoretically interesting in terms of like the theory of language or fundamental things about LLMs. So I just would dissuade you from trying, honestly. I just would say, don't do that. And we should, and there's a broader big point. We should insist on you, for research purposes, using open models. And open models means access to the direct probabilities, access to the internal representations, the embedding representations, and really, ideally, access to the training data. Because without those, we don't know what we're working on. And why is it scientifically interesting to work on things that, you know, what are we going to learn that's generalizable if we don't have access to those things? So we have to insist in the research community on the openness of the tools that we're working on and that we're working with and that we're developing. So maybe I'll stop with that because I think that's a really important message that I didn't have a chance to highlight during the talk itself.
Okay. Thank you very much.
Everybody so much.